Okay, so the last time we met, we were looking at thermodynamic relations, and I said I would say something about this question. So, if you are actually new to this part, you can go to the previous video, yes, the part one, and then you can go through everything so that you get the understanding of this part. So, what we were talking about was this question, and everything we said was actually fine. So, this was the expression we had for dv. Once again, not del v, it's dv being equal to this whole expression we have down here. And we're able to simplify it to r over p dt minus rt over p squared dp. And I was saying that realize that in this form we have here t and p. We don't have t1 or t2, we don't have p1 or p2. So what we can put in here is the average value. Because t and p are not so far from each other, it will give us something that is quite accurate, right? So we can rewrite this as r over p t2 minus t1, as I said. Then r, sorry, this minus, so minus rt on p squared p2 minus p1. So realize that t2 minus t1, so that's 29 degrees Celsius minus 25 degrees Celsius. That will give us 4, right? Even if it's in Kelvin, it will still be 4. Then minus RT on P squared. So P2 was 1, 2, so it was 120, and P1 was 122, so it will be minus 2, right? So if we should express this, we can put in the average P for the P values and the average T, which we found over here. So it's just going to be this one we had it by doing T1 plus T2 over 2. Same thing for the pressure, P1 plus P2 over 2. Right. And we said we are using R as 0.287 because we want to answer in meter cube per kilogram. If you want your answer in meter cube per mole, you can use R as 8.314. So when we put all of these things inside, we will end up getting this answer for dv. So you can try to realize to get the same answer. And then we said that if you are looking at finite change, the delta v, then we look at rt over p final minus rt over p initial. So I can, in this case, I can actually put in my t2 and p2, my t1 and p1, and I'll end up getting the same value. So you realize that the values are actually quite close to each other. Okay, for today, what we call the Maxwell relations, and we are going to deal still with our partial differentials and all of that, right? But before we start that, there are four relations that we need to have in mind, and four relations that are very fundamental to this aspect of the course. So these are equations that you should have seen before, especially equations 1a and 2a. For equation 3, it is not to gives energy, right? H is our enthalpy, U is our internal energy. Right? And then maybe I can express this as m dz plus n dy. If you look carefully at all the expressions we have, they follow this kind of format. So for the u, for equation 1a, for example, we could have said that maybe u was a function of maybe s and v. So du was equal to um del u del s at constant v ds plus del u del s at constant sorry del u del v now at constant s rather dv. So I can relate this to the t from equation 1a, and I can relate this to the minus p from equation 1a. So they are following the same format, right? Now we also spoke about exact and non-exact. So we spoke about all of this before. We spoke about the exact and non-exact. So we said that yes, z is a function of x and y. We can represent dz as this, and then we can write it in the differential form to have m dx and n dy, like what I said earlier from this slide. So we can actually express maybe this whole expression as something else, m t, anything, like depending on what we are working with. So we'll see as we go along, and then we can have this expression also expressed as n. Now we also said that if we want to show that they are exact, then it means that I can take the m expression and rather find its partial derivative with respect to y. So initially, to get m, I found the partial derivative of z with respect to x. I want to do the whole thing, the whole m expression, but rather with respect to y when I'm keeping x constant. So to really get the understanding of all of this, I feel it's better to go to the previous video, especially the beginning part, because we spoke about all these things, right? And how we can prove it with um, these forms as well. Okay, so we want to or one thing we'll point out is that using all those exact and yes, the exact expressions, right, we can change equation 1a, or we can derive from equation 1a equation 1b. From equation 2a we can derive 2b, and so on, right? So I would use what we have from equation 1a as the example. We said that from equation 1a, what we did over here, I'm picking this expression here, what we've done over here, right? So du is del u del s at constant v ds plus del u del v at constant s dv. So I'm going to pick that expression and use that in this case, right? Or is I think it's even, yes, it's better this way. So we also said that we can express the del u del s at constant v as t, and then the del u del v at constant s as minus p. So we rather work with it from this perspective. So we said here that du was equal to t ds minus p dv. So we work with it this way instead, right? To show that we are working with something exact, we can take del t. So modeling it after this, where we took del m del y, from here we took this value here, found the partial derivative with respect to the other variable, right? And then we took the n as well and found the partial derivative with respect to the other variable. So here I'm going to take t, find the partial derivative with respect to the other variable, which is v. Well, but this time I'm going to keep the variable that it was originally with is now going to be kept constant, right? We are saying that for it to be exact, that should be equal to. Now I'm going to take the p. So there was a negative, so del p, and now with respect to the other variable, which is s, right? And this time the variable that it was with will now be kept constant. So that's how we are working about it. So if we pick maybe equation 2a, for equation 2a we had the expression for dh. So we said dh was I think we said it was tds plus, was it vdp? Let me verify. Yes, vdp. So plus vdp, right? So I can take the t, so del t, then the other variable from the other part of the expression, so with respect to the change in p, and now the variable it was with, I'm going to keep that one rather constant, a constant x. That should be equal to, now I can take the v, so del v, and do it with respect to the variable at the other side, so del s, but this time at the variable that is with will now be the constant, a constant p. So that's how we get equation 2b. So that's the understanding behind it. When we express it in the form, if we have any expression like z dz is equal to m dx plus n dy, what we are saying is that we can take the m, express it as a partial derivative in terms of y instead, and keep our x constant, right? And then we can equate it, or it will be equal to, if we rather took n, expressed as a partial derivative of x instead and kept y rather constant. So that's the general um structure behind this. Now there's actually a short, so we can actually find from equation 1a 2a 3a 4a all the way to equation 1b 2b 3b and 4b. To find the so from equation 1a to 4a, right, we work with the we work with the letters in the middle, these ones. So if I pick u, that will be, oh, where should I write it? Okay, that will be du. is equal to, and I go to the opposite side of the rectangle, so that's this side, right? So I'm here now. I'll come to the opposite side, that's this side here, and look at the values at the corner. So it's P and T, so I can put them down. So I can put P and T down. Now what I'll do is that from P, right, I'll trace it back to what was to the side where U was. So I'm going to trace it back here. So the P is going to go with a dV, right? And then from the T here, I'll also trace it back. So the T is going to go with a ds. Now from this arrow we have down here, if I end at the arrowhead, I have to negate it. So when I did P dV, I ended at the arrowhead, so this has to be negated. So it means that my du is TdS minus P dV, and that's what we saw over here, TdS minus P dV, right, for equation 1a. So I'll use another example so that you can get it a bit more. So let's try it with H now. So if I want to find dH, I come to the opposite side, right? So H is here. I come to the corners at the opposite side, so I'm coming to V and T. So I can write my V and T down. So there will be V, there will be T. Now from V, I'm going to follow the line back to the side where H was, but in the corner. So it's going to be a dP. So V will go with dP, right? And then my realize that it's not where the arrowhead is, so it will be positive. Then I had T as well, so when I trace it, T is going to go with ds, but it's also not where the arrowhead is, so it's also going to be positive. So dH is VdP plus TdS. So that's what we have here, VdP plus TdS, right? So now we can try it for A as well. So if I want to find dA, right, dA, I'm going to go to the opposite side. The corners, this is where A is. The corners are the opposite side. So this is the opposite side of the rectangle. The corners there are S and P. So I write down those values. So I write down my S and my P, right? And now I trace it from S and P. I follow the line back to the line, the side where A is. So I trace it from S down. So I'll have a DT. So it's S DT. But it ends where the arrowhead is. And realize where the arrowhead is, we said it's negative. So it will be a negative here. And from the P as well, I'll bring it down to this side, right? So it will be also minus P, then dV. So that's what we have for dA. It's minus S dt minus P dV. So that's what we have over here. And finally, we can do the same thing for dG. So if we want to do it for dG, G is here, the opposite side is here. So the corners at the opposite side are S and V. So I'll write S and V down. Right. Now I'll trace it. So from S, if I trace it, I end at T. So it is S dt. It ends where the arrowhead is. So this is negative. And then from V, I can trace it back to the side that G was at. So it will be V dP. There's no arrowhead here. So this is positive. So dG is V dP minus S dt. Right. And that's what we have here, VdP minus S dt. So that's how you can use the rectangle to find equations 1a to equations 4a. So you have to be able to do this. And please, if you are drawing the rectangle, don't mix up the letters. The moment you maybe switch S and P, you make a lot of mistakes. Now we want to look at how we can do this for also quite interesting. For this one, we don't work at the we don't so let's say I'm starting with S, right? I want to start with S. So I'll take it first, I'll take it I think this is counterclockwise. So I'll first take it counterclockwise, then I'll take it clockwise. So you understand what I'm saying very soon. So I'll start with S. So I'll have del S. Then I come counterclockwise, so I go to V. So del V at constant T. So I'm going once again anti-clockwise. So I'm starting with S, del S, then del V at constant T. is equal to, so I now start at the next value, so del p, but then this time I go in the reverse. So now I'm going this way now, so del p del t at constant v, right? And that's going to give us oh, sorry, I forgot to even mention this. So we did del S, del V at constant C. Once again, it ends at an arrowhead, so this will be negative. And then we did del P, del T at constant V, ends at an arrowhead, so this will be negative. So negatives can actually cancel out. So we are going to have equation 3b from what we just did. Del S, del V at constant T being equal to del P, del T at constant V. Right, so the negative cancels out. Oh, sorry. This was supposed to be del S del V, right? So that we have the expression in this way. So I'll take it again. I think I'll take it a bit more slowly. So what we are saying is that wherever I'm starting from, whichever corner I'm starting from, right, I first move anti-clockwise until I've used all the letters at the corner. Then I move in the opposite direction. So if I'm starting with S, I'll start with del S, then I come anti-clockwise. So I'm now going to V. So del V at constant T, right, is equal to, so I've not used all the letters here, so I'll go to P. It's equal to del P. So now that I've gotten to P, I'm not going to go back to S. I now go in the reverse. So del P del T at constant, once again in the opposite direction, at constant V. If I end where an arrowhead is, I bring the negative, but they can cancel out. So this was equation 3b. So we can try this starting from another tip. So let's start from where V is. So if you are starting from where V is, I'm starting from here now. So it will be del V, and I move this way. So del V, del T at constant. So I'm moving this way now. P is in the corner. Is equal to, I've not used all the letters here, so I can come back here. Is equal to del S. So now I've used V, T, P, and S. I can now move back. So is equal to del S, del P, and then once again I come back at constant T. Right, now let me check for my arrowhead. So it was VT at constant P. There's no arrowhead here, so this is positive. Where I ended for the first one is positive. And I did SP at constant T. So where I ended at constant T here, there's an arrowhead here, so this is negative. Right, so this expression is similar to expression 4b. Del V del T at constant P, that's what I have here at the left hand side, is equal to minus del S del P at constant T. That's what I have at the right hand side. Right. Okay, now we can try this. So let's start at T instead. So now if I'm starting at T, right, I'll have del T, and now I move to P, anti-clockwise still. So del T, del P at constant S, right? Then I come, so at constant S, there's no arrowhead here, so it's positive. Is equal to, I have to now include the last um symbol. So del V, now I can go in the reverse because I don't want to, come back again. I've used all the letters. I can go in the reverse now. So del V, if I'm going in the reverse, del S at constant P. Once again, I'm not ending at an arrowhead, so this will be positive, and this will give us 2B. So del T, del P at constant S, that's the left hand side, is equal to del V, del S at constant P from 2B, that's the right hand side. And finally, we can start from P, and we'll end up getting equation 1b. So if I'm starting from P, it's going to be del P, then del S at constant V, ends at an arrowhead, so negative, is equal to del T. So I add the last letter and I go in the reverse now. Del V, so I'm going the reverse now at constant S in the reverse. So this is going to be what I have here. So I have del T, del V at constant S, that's the left hand side here, is equal to minus del P del S at constant V. So that's what I have here for equation 1b. So you can use this to generate all those expressions. Now the reason we are doing all of this is because in reality it's not easy to directly measure entropy, enthalpy, and internal energy. Right? If you have a system, it's easier to measure the temperature of a system than say you're coming to measure the entropy of the system. So if we have any expression like something like this, del S del V at constant T, because we can't easily measure the change in entropy, We might want to rather express it as this form instead, because we can easily measure pressure and temperature, right? Or maybe this expression over here, equation 4b, it's not easy to measure del S. It's not easy to measure the change in entropy, right? So what I can do is I can rather equate it to terms I can measure, that's volume and temperature instead. So that's why we are doing all of these things. So we are seeing that it's not easy to directly measure entropy, enthalpy, and internal energy. So these relations help us to relate their changes. If we want to find the U, we want to find the H, we want to find the S, we can relate their changes to changes in terms like pressure and temperature and volume. So we can find the T, the P, the V, or del T, del P, del V. Any of these things are easier to find than finding it in terms of entropy, enthalpy, and internal energy. So that's why we are doing all of these things. Okay, so now let's take a few cases. We are going to start with internal energy. So we are seeing the internal energy as a function of temperature and volume. We want to consider it as a function of temperature and volume. And one thing to notice is that you can have something as a function of more than two things. You could have looked at maybe you as a function of maybe rather pressure and um, temperature, right? But sometimes um the variables we decide to express term as a function of might make it hard to work with it. So we'll see as we are nearing the end of this particular lesson. We'll see as we are nearing the end. So for now, we are just going to consider that U is a function of temperature and volume, right? So our du is going to be, because I think by now you should be able to do this. So du is del u del t. We are changing with respect to t while we are keeping v constant, dt plus. We are changing u with respect to v when we keep t constant, dv, right? And realize that this expression here, what is over here, is the same as cv, because you're looking at a heat capacity. You're looking at how our internal energy is going to change with temperature. So if I have del u del t, right, at constant v, because I'm looking at how my internal energy is changing with temperature, it's going to be a certain heat capacity. But realize it's a constant volume. That's where we are getting the cv from. When we are looking at the expression for cp, we realize that it's actually I think it's del h del t at constant p. So you're looking at how enthalpy will change when we are changing temperature when we keep pressure constant. That gives us the heat capacity considering constant pressure. So that's our cp. So would actually talk about these things because they are very important to this course. So we are saying that what we have here, the del u del t are constant v is cv, right? Now remember that we also said du was tds minus pdv, right? So now let's compare equation 5 and equation 6 now. Realize that from equation 5 and equation 6, there's a dv here, there's a dv here, so that's fine. But we have a dt here and we have a ds here, right? And remember we said that we don't want to express or we don't want to have our expressions in terms of things like entropy, enthalpy, internal energy. Here we are looking for change in internal energy, so that's fine. But we can't easily measure the change in entropy, so we can use a different expression to represent that. So what we are going to do is that yeah, so as I said, we have dt with one expression and ds with the other. It's more practical to measure the change in temperature directly than the change in entropy, right? So we can express ds now. We can change this ds to be in terms of to be, I mean, to have or to have a relation with dt, right? So that we can replace ds in equation 6. Now we want s to also be a function in terms of the things we were changing in equation 5. So in terms of t and v. So we'll make it in terms of t and v so that we can end up getting dt and dv back in our expression. If we made s maybe a function of t and p, we end up getting dt and dp. But from equation 5, we don't have dt and dp, we have dt and dv. So because we want to be able to group terms at the end of the day, we'll make s a function of t and v. We are considering s as a function of t and v. So what is going to happen is that once again we'll have our normal expression. So s as a function of t and v, we can express the s in this form, and we can replace the s in equation 6 with that expression. So we have equation 5, equation 6, equation 7 is the expression for ds. So I can replace the ds here with equation 7. right? And that's going to give me equation 8. So du is going to be t times ds, which is all of this, minus p dv. Now I can group my terms. So if I should expand this part here, I'll have my t del s del t as constant v dt plus my t del s del v as constant t dv, right? Now I can group terms. So I can group the terms with dv. So I have all of this. That's if I expand what I have here, minus p dv. So the terms with dv are this one and this one. So I can group them and then keep dv out. So that's going to give me this part here. I'll have my t del s del v are constant t. That's this, minus the p all times dv, right? And then this expression here, this part here, the t del s del t are constant v dt becomes this part here. Now remember, if we compare, let me clean all of this because the screen is a bit messy. Remember that we said from equation 5, we said that del u del t at constant v, we can say it is cv. Now if we compare equation 8, now equation 8 is now, equation 8 is now du is equal to all of this. If we compare with equation 8, now realize that the coefficient of the t, right, should be the same thing as that in equation 5. So it means that this is also equal to this expression over here. So I can write this as t del s del t at constant v. So we'll see the essence of this later on, right? So I kept it in yellow because we'll need it later on. There's a point where you have an expression, or you see just del s del t at constant v, right? So you can express that expression because, okay, you can express that expression as cv on t, right? Just this part here, I can make it cv divided by this t to get the s or t at constant v. The reason is that this expression is not, we don't have any other relation for that del s del t at constant v. So you can check it here. There's nothing like um del s del t at constant vs. If we check it, we won't see that here. So we can check it to see if we have a Maxwell relation for that, and we don't. We don't have del s del t at constant v, right? So we can't use any Maxwell expression to change the del s, because once again, we don't want to be working with entropy, or we want to work with things that are more practically easy to measure, right? So we can't get a Maxwell relation for this. So how to end up using cv on t? That's why that expression is what's about. We'll see the essence of all of that as we go on, actually. So we can put this on hold for now, but then it's something important to keep in mind, right? So we are comparing equation 5 and equation 8. So we said the coefficient of t in equation 5 should be equal to the coefficient of dt in equation 8. So we said that the we said del u del t are constant v here should be equal to t del s del t are constant v here. In the same way, we can equate the coefficient of dv in equation 5 the coefficient of dv in equation 8. So del u del v are constant t here will be equal to this whole expression, the t del s del v are constant t minus p. So that's what we have down here, right? Okay, now from the Maxwell relations, we can actually get an expression for del s del v are constant t, right? So for that one, we said del s del t, sorry, the expression was del s del v, sorry, are constant t. So that's this expression here, 3b. Del s del v are constant t. We can replace it with del p del t are constant v, because once again, we don't want to be working with entropy, right? So we can replace it with del p del t are constant v. So this expression in here, right, which we said was, we equated the two of them together, the coefficients of the v. We can replace that del s del v are constant t with del p del t are constant v. So that's the Maxwell relation, right? So that we can work with values that are easy to measure. Okay, now okay, so I think, yeah, so we started with du to be this, and we said we wanted to, once again, we can't easily measure just the changing. We're looking for the changing internal energy. We can't have a change the partial change in internal energy in our expression. So we express it in other forms. So we ended up changing this part here to cv dt, right? So that's what we have down here. This was what we had from the equation 8, what we have down here. So we ended up expressing it as dv dt plus this whole expression down here. So now it's in terms of p and t, right? So now everything we have here for du is in things we can easily measure, right? So we said we want to be able to measure the change in internal energy by looking at changes in parameters like temperature and pressure. So equation 5, we still had a partial change in internal energy in the expression. That's what we have here, right? Which we don't want to work with. So we simplified it to this form, this whole expression here, right? And we said that we can write it as cv dt plus all of this. So now it's in terms we can easily measure. We can determine cv, we can find a change in pressure, we can find a change in temperature. It becomes something easy to work with. So this is going to be our final equation that we'll be working with. Now what's going to happen is that when we are given a particular equation of states, then we can do the differentiation, right? So we've been given let's say we've been given the ideal gas equation, consider one mole of the gas. We have P is equal to, we want to look at how P from this expression in here, we look at how P is going to change with respect to T when we keep P constant. So when we say that we need to make P the same, we want to look at how P is changing with respect to T, right? So P is going to be equal to RT over V. Now remember we said that now we are keeping V constant, so I can express my R over V as a constant. So V is a constant times T. So if I want to find del P, del T, a constant V, it's a constant times my variable. I'm just going to be left with the variable, right? Sorry, I'm going to left with a constant. Sorry. It's going to be my C, and we said that C was our R over V. So if we find that expression, we'll have our R over V. So as I said at the start of this video, that we need to be very conversant with how to work with partial derivatives when you are given expressions, right? So once again, we're looking at how P is changing with respect to T when we keep V constant. So we can make P the subject in our equation of states, and then we are looking at how P changes with respect to T. So R and V are constant. So if I should do the differentiation, R and V are a constant, multiply my variable, right? I'll have the constant still there, right? Or if you like, we can even make this easier. So I can say this is T to the power 1. So if I'm doing my normal differentiation, I would have brought this number down. So 1 will multiply this. Then T to the power 1 minus 1, or T to the power 0. And T to the power 0 is 1. So I'll end up just having R over V, right? So anything that makes it easier for you to grasp it, but you have to really practice partial differentials, and I think you would have done that in differential equations and a bit in multivariable calculus as well. Okay, so yes, our del P del T, a constant V, we said is going to give us R over V. So I can replace this whole expression here with R over V, right? And that's going to give me this expression here. So the T will now multiply R over V to give me the T R over V in this expression down here. But remember that equation of state said PV is equal to RT, and we said P is equal to RT on V. So the is the same as TR on V. So the TR on V we are having here is actually going to be the same as P. So in effect, this is the same as P minus P, which is 0. So I'll end up having my du to be equal to cv dt plus 0, which is just cv dt, right? So one thing to note is that it doesn't always cancel out. It depends on your equation of state. This is cancelling out because you're dealing with an ideal gas. You're using the ideal gas equation of state, right? It wouldn't always cancel out. It's canceling out because you're using the ideal gas equation of state. And for an ideal gas, yes, du is equal to cv dt, right? Okay. If you had maybe Van der Waals or Peng-Robinson, it wouldn't be as straightforward as this. Okay, so we looked at internal energy. Now let's consider enthalpy and entropy. So we can look at enthalpy as a function of temperature and pressure. So the H is going to be del H del T are constant P dt plus del H del P are constant T dP. We've seen how to go about all of this. But from our equations, what we did at the start of this video, we said the H is equal to this. So that's equation 10. So following the same format for the internal energy, what we did, we see here that I have dP and dP, but I have dt and ds. So I want to change the s to something with t and p, so I can make s a function of t and p, because we don't want to be working with change in entropy, right? So s as a function of t and p. So I can express the s as this and then replace the s in equation 10 with that. So if I do that, we had equation 9, we had equation 10, we express the s to get equation 11. So I can put equation 11 in equation 10. So I have dh to be equal to vdp plus t, then the whole expression for dx, sorry, ds, that's equation 11. So I can put equation 11 in here, right? So equation 11 to have this expression down here. Then once again, I can expand and group the t's and the dt's and the dp's so that I have my dh. This if I do the expansion and the grouping, right? And I can simplify it to this form. So once again, you realize that we are going to end up getting or even before this, let me talk about this side here. Remember we said this expression here, if I'm looking at my change in enthalpy with respect to change in temperature at constant pressure, it will be Cp. So we'll have that to be equal to Cp, right? And that's the coefficient of the T. So once again, we are coming to compare the coefficients. So we have um the if I compare equation 9, let me clear the screen a bit. Let me write this out again. So from this part here, I have my dh to be equal to, if I should write the raw expression, if I should use this expression down here, right, it's going to be the t del s del t at constant p dt, right, then plus um v plus the t del s del p at constant t dp. So I'm just rewriting what we have down here. Now we compare equation 9 to this, right? So I see that the coefficient of dt here should be the same as the coefficient of dt here. So that del h del t at constant p, this one here, should be equal to this expression here. And we said that this was equal to cp. So that's what we have down here. Del h del t at constant p is equal to the t del s del t at constant p, right? And that's going to be equal to RCP. Then I can also compare the coefficients of the dp, the coefficients of the dp here, so that del h del p at constant t becomes equal to this whole expression down here, right? So I think that's what I did at the, oh, I didn't do that on the next slide, but then that's what the expression is going to be, right? So it's going to be v plus t del s del p at constant t. And once again, we don't want to work with del s, so I can use a Maxwell relation and end up changing this to what I see over here. So del v del t at constant p instead of del s del p at constant t. So if you check, we have a Maxwell relation for that. Okay, now we are coming to consider entropy with three cases. So earlier I was speaking about the fact that we could have expressed maybe internal energy in terms of other things, right? So now we are coming to look at what happens when we express entropy in terms of first temperature and volume, then temperature and pressure, then volume and pressure, right? So if I let's even start with the volume and pressure one. So I said here that we could have done the same thing with internal energy and enthalpy, but as we will see, not all the relations will be easily simplified into expressions that have terms you can easily measure, because not all the expressions we'll get would be things we can use the Maxwell relation to simplify, right? So for example, if we start with s as a function of v and p, we're going to end up with this. Now realize that we can't simplify this with any of the expressions we have, because we won't be able to relate it to any Maxwell relation. You can actually check the Maxwell relations. You won't find anything like del s del v at constant p, or del s yes. So I think yes, you also not find anything like del s del p at constant v. So we can't simplify this further, right? And the thing is that we still don't want to work with del s. So expressing s as a function of v and p to find a change in s is actually not going to be so convenient for us, right? So as I said, yeah, we can't simplify this with any of the expressions we have, and we to still have del s in our expressions because this form is not so useful to us. So with time, you actually get familiar with the most useful expressions to work with. Now, if we are doing it with respect to t and v instead, we are going to have this expression, right? And remember, we said that del s del t, or from the equations we had when we were expressing CV, we said that del U del T at constant V could be related to this when we're dealing with the internal energy part, right? And we said that it was equal to CV. So it means that this is equal to CV. So if I want just the del S del T at constant V, it's going to be CV on T. So I can replace that expression with CV on T to get this part. Then you realize that I still have del S in this expression. So I want to use a Maxwell relation. For this one, I can actually find the Maxwell relation for del S del V are constant T. So that will be the del P del T are constant. So we can check it out and then we'll get this. So when we are done, if we want to find maybe our S, so maybe S2 minus S1, we can integrate both sides. So that we'll have here integral of CV on T dt plus then this expression. So maybe we have an equation of state. So we can use this to model our equation of state so that we'll have that expression, check all of that expression dv. So maybe from so this t, maybe from t1 to t2 and then from v1 to v2. So that's the general idea behind what we do over here, right? And when you end in this form, you'll be given an equation of state you can use to model this part, and then if required you just have to integrate everything to get your values. Yes. Or if integration is not required, you can use what we did earlier. If you're supposed to find the ds, you could use maybe t2 minus t1 for the dt part and then v2 minus v1 for the dv part. It depends on how much accuracy you are looking for. Okay. Now, if you are expressing entropy in terms of temperature and pressure, we'll have it in this form, right? So once again, you should be familiar with this by now. And then remember, we also said that del H del T our constant P was equal to this expression down here, and then we said that was equal to Cp. So if I want just a del S del T our constant P, I can make it Cp on T to get this part here. And then once again, the del S here, we don't want it in there, so we can express the del S del P our constant T with a Maxwell relation to get the minus del V del T our constant P. Then if need be, we can integrate both sides, or we can just express the dt as t2 minus t1 and the dp as p2 minus p1. So we'll take an example from Shom's. It says that we should derive an expression for the enthalpy change in an isothermal process of a gas, for which the equation of state is this. So they've given us the equation of state to work with. So for the h, right, we won't go through the whole proof, but remember we simplified the h to this form. So we can go back to that, but we simplified the h to this form. And mind you, we said it's isothermal, so it means that temperature is constant. There will be no change in T, so the T is 0. So you can actually express the H in this form. But the thing is that, okay, before that, we have here our del V del T our constant, and we've given an equation of state. So you realize that for us to find a change in volume with respect to the change in temperature, as we are keeping pressure constant, we need to make V the subject in our equation of state. But this is going to be very difficult to do, especially because we have V here and V squared here. So what we can do is that we can now look at expressing this in a way that we would have del P instead, right? Looking at the change in pressure instead with respect to something because it's easier to work with. So what we can do is that instead of us starting directly from the enthalpy points, we can start from this expression where H is equal to U plus PV. Now you might be asking that, oh, how would you know you're supposed to do all of this? The thing is, it actually comes with practice and experience. So as you, practice these things, solve more examples, when you are faced with the question, you will know what to do. Okay. Now, PV, right? Now we know the expression for, okay, before we go there, the PV, we can represent it with P2V2 minus P1V1. So we can keep that side out for now. Let's focus on just the du, right? We know the expression for the du, what we found earlier was also this expression. And we have our equation of states. Now we have this term instead, del P del T are constant V, instead of del V del T are constant P. And we can easily simplify this now because now P is already the subject here. So we just look at what happens when we look at the change in P as T changes, but we are keeping volume constant. So if volume is going to be constant, then if I'm supposed to do my differentiation, Volume is a constant, B is a constant, R is a constant. So I'm differentiating once again my constant times T. But I want to do with respect to T, so I'll be left with just the constant. Right? So I'll end up getting R over V minus B for that side. That's what I have here. Here there's no T term multiplying it, so it's just a constant. If I differentiate just a constant, I'll get 0. So it is plus 0. So the del P del T are constant V, I can represent it with R over V minus B. So I can replace that I can replace this here with R over V minus B. So if I do, my du part of the expression becomes CV dt plus T R over V minus B minus P. Right? And I can bring in my P to V2 minus P1 V1. So it's the same expression we have here. But remember, there's still a P in here, right? And we had the equation of states to be this. So I can replace the P here with that. So if I do, I'll have the T R over V minus B minus this whole expression. So it's going to be minus RT over V minus V. This was supposed to be plus because it's minus the whole expression. So plus alpha or A over V squared, right? So if I should do this, realize that now I'm going to have RT from this side, RT over V minus B minus RT over V minus B. So these two terms can cancel out each other so that I just end up with CV dt plus A on V squared dV, right? So that's what my expression is going to be. A second, let me, whether I was supposed to be plus, yes, it's plus A on V squared. So that was a mistake from my side. Yes, so this is supposed to be plus, right? So we are going to have the expression in this form, and then we can simplify if we have to do our integration or work with our changes or anything. Yeah. Okay, so that will be it. Thank you for your time.